Hello and welcome to the Sensibly Speaking podcast. This is Chris Shelton, the critical thinker at large, coming at you across a multiplicity of platforms with real podcasting amazingness and excellence. So with that all being said, let's get right into it. This week, I am bringing on an actual neuroscientist. This is going to be awesome. Actually, I hope that this will be the first of many shows because neuroscience is something that I got really interested in last year in the chain of research of psychology, sociology, and then, wait a minute, what's going on up here? And so I am now enlisting the aid of neuroscience to assist me in talking about how we think, critical thinking, and cult thinking, kind of polar opposites of thinking there, but it's all going on up here. And what is going on? How is it going on? Is it important that we understand it? I think so. And maybe it could actually improve our day-to-day lives by knowing more about what's going on 2 inches behind our forehead. So that all being said, welcome to the show, Dr. Jonas Kaplan.
Thank you. I'm happy to be here. I think this is extremely important.
Yes, I do too. I'm glad that you are joining me for this. You are a doctor of neuroscience at USC, is that right?
That's right. I'm a cognitive neuroscientist, so I'm in the psychology department at USC. I study how the mind works and how the brain supports what the mind does. I mainly use brain imaging technology. So, excuse me, I use a technology called fMRI, functional magnetic resonance imaging, where we measure what's happening in the brain while people do various things to understand their psychology and how the brain decides what is true, how we believe what we believe, how we change our minds in response to new evidence have all been topics that have interested me quite a bit recently.
Excellent. Yeah, you've when we spoke and initially in our emails, you had expressed interest in cults as well. So I think we'll be sort of feeding each other here, which I think will be great.
Well, just one of the other topics of research in my life. I'm sorry, it's a little bit of delay there. Is where the self comes from in the brain, and the concept of self and how we connect ourselves to other people is one of the phenomenon that cults really bring to mind, and that's why I've been interested in them.
Big time. I have been very, very interested in that topic in the last couple of years, wondering about free will, consciousness, personality. I've done, a bit of reading, bit of looking into this. David Eagleman's Incognito, Lisa Feldman Barrett's How Emotions Are Made. There's a wonderful book I'm reading right now whose the name of the man escapes me, but it's a Skeptic's Guide to the Mind. I think Robert Burton or something like that is his name. So this has been a real interesting topic for me because I've been trying to figure out what makes us tick. And I'm sure I'm the only one in all of history who's ever wondered this. So, and it kind of led to neuroscience, and I've had some interesting ups and downs with this in terms of thinking about, well, is the brain causing things, or is it responding to things? Is it just a reactionary organ, or is it actually like proactively, making things happen, seconds, minutes, milliseconds before we're quote unquote aware of it? How does this thing operate? And I think by understanding as much as we can, at least as, getting out to the cutting edge or bleeding edge of where we're at with neuroscience, maybe we can find some answers or see where the answers are leading to why we think the way that we do, how we think the way that we do, and maybe some of the aberrations in our thinking when we think about cults, or extremism, or, going all in on things we shouldn't be. I don't want to spend too much time, especially in a podcast, on anatomy, but I kind of thought we might need to start with some first principles and basics with this. What would you say from your position, your sky high sort of, big perspective view of this? What do you think are the important things for lay people, non-neuroscience people, to understand about this organ in our head?
Well, the anatomy is not unimportant. I mean, it is important to understand a little bit about the anatomy because the function kind of maps onto the anatomy a little bit, right?
Mm,
Understanding what the different parts of the brain are, how it all fits together, what the pieces are, I think that's all really important to understand. And, you can think of the brain in some basic conception of it as a biological computer. It is a computer in the sense that it's processing information, it's building models about the world, it's helping us to perceive what's out there. But it is a biological computer. It's not the same as a physical computer in that it's not, number one, it's not built on silicon. Um, but there are a lot of differences between a real computer and a biological computer that are important. Mainly, um, you know, if you think about what the purpose of the brain is really a big, important solution to the problem of how to keep us alive. It is
mm.
part of our body and part of a living system. And the brain's main goal is to be really smart about keeping us alive, keeping us away from danger, helping us to find the things that we need to maintain our homeostasis, to keep us within a certain temperature range, to keep us within a certain balance of energy, to find food. And to solve all those problems, the brain is incredibly good at doing that. But that is really underlying absolutely everything else that the brain does. And so when we think about higher cognitive functions, and we start to talk about things that we'll talk about later on in terms of decision making and belief formation and connection with other people, all of those things are resting on top of this underlying motivation that the brain has to keep us alive. A computer, a regular computer, an artificial computer, doesn't have a motivation. It's really just processing information according to some program. But the brain is always motivated, number one, to keep us alive. And then there are a whole series of layered motivations on top of that that relate to that ultimate motivation to keep us alive, that are constantly driving our cognition. That's one of the really important things to keep in mind.
Yeah, big time. And I think it was a real perspective change for me reading Feldman Barrett's take on this in terms of describing the brain as an organ that regulates the systems of the body. And its primary function is regulating the systems of the body, which fits right in hand in glove with what you just said. And but it was a perspective shift for me because most people, at least certainly, well, I'll stop projecting my ideas on everybody. I certainly thought that the brain evolved to think, or the brain evolved to have rational thinking, or to figure out problems or something. But this was a big perspective shift for me to realize, yeah, no, that's a very, very tiny percentage of what's going on up there. Most of what's going on, or I guess I should ask, is it accurate to say that most of what's going on up here is a regulatory process? How much blood's going into this part of the body versus this part? What neurotransmitters do we need to fire down in here to do this, and what about this, and sort of regulating. You imagine a bunch of dials and levers and things.
Yeah,
Is that accurate?
well, here's where something about the anatomy can help us to map this out a little bit. So, if you think of the brain as extending from the spinal cord, the very bottom of the spinal cord basically balloons up into our brain. And as you move from the bottom of the brain up to the top of the brain, it's kind of like you're taking a journey through evolutionary history from old to new. The older parts of the brain are at the bottom, they're closer to the spinal cord. Those are the parts of the brain that we tend to share with much older and simpler creatures like fish and reptiles and birds. And then as you move up, you get more and more complicated and evolutionarily newer parts of the brain that we share with other mammals or with primates or with only chimpanzees, for example. And
Mm,
those lower parts of the brain, the parts that are closest to the body, are the ones that are most involved in the basic regulatory processes, keeping us breathing, keeping our heart rate going, keeping our temperature, motivating us to find food and sex and the other basic things that we have instincts for. And then as we move up into the newer and newer parts of the brain, you start to see more complicated things happening, regulation of emotion and feeling, and eventually decision making and thought and language. And so it's hard to say what the brain is mostly doing, but certainly these older parts of the brain, the original parts of the brain that are still an important part of us, are concerned with as you say, regulating the organs of the body. And the reason we want to regulate the organs of the body is to keep us alive. That is ultimately the goal that we have to keep in mind.
Yeah, exactly. Um, and I guess you could say, I mean, everything in our body is there to help keep us going or keep us alive, and different things have different purposes to it. So I guess when we think of the brain, we think of it as a coach or a quarterback or the guy who's sort of, doing the long range planning or something when we analogize, as opposed to the liver, which is like this great big filter or something, and these kind of things, or, lungs with the air. So isn't that, is that all it's doing is sort of just regulating this stuff, or is there some other function going on there too?
I mean, a lot of cognitive function doesn't fall into that category, right? So we can
Right.
certainly, it's important to remind ourselves how connected we are with our evolutionary history and the parts of the brain that are similar to fish and reptiles. But then we also have these parts of the brain, the newer parts, that are very, very different and allow us to almost disconnect from that moment-to-moment regulatory activity and to travel in our minds to literally other times and places. I mean, we can think about what happened yesterday or 2 weeks ago. We can imagine what's going to happen tomorrow. And that ability to mental time travel is one of the most amazing things that the human brain can do that other kinds of brains can't do. So, we also language, language is one of the things that's uniquely human, and to formulate symbols and to put these things together into stories that transmit information to other people. Those are also unique to humans, and also extremely important for our experience of being alive and being humans.
Yeah, totally. Well, okay, so anatomy wise, I guess the basic building block of this, when we think about, when we analogize it to computers and programming, or computers and machines and stuff, which I think we need to keep in mind is a limited analogy. It's not exactly a computer, it's not exactly a machine. It's vastly more complex than either of those things. But as an analogy, it works. Would we say that neurons are the 0 and 1 determinators? Are they the on off switches of the brain, or what's the analogy there?
Yeah, I would say the neurons, that you can see them right behind me there, are more like
Yes.
they're more like the transistors, and like a artificial computer, they do generate electrical impulses, the electrical signals. And in the neuron, there's a special kind of a signal. It's called an action potential. An action potential is an electrical signal that the neurons send, where suddenly the voltage in the neuron goes up and it goes down. So you get a big spike of electrical activity.
Okay.
And it is very much like a 1 or a 0 in a computer, because either it happens or it doesn't. It's an all or none phenomenon. You never get half an action potential. So it is like in that sense, like a binary code. The neuron can fire an action potential at any given moment, or it cannot fire an action potential. And so in that way, there's a close analogy between a computer and a neuron. In other ways, the analogy breaks down. So neurons connect to each other. They form, as you say, it's a massively complex system. We have 100 billion neurons in our brains. I mean, that is an enormous number, right? There's probably,
as far as I understand, isn't that more than the number of observed stars?
There's probably about 150 billion stars in the Milky Way. So it's on the order of some galaxies have 100 billion stars. And, there's only maybe 1 or 2 people on Earth that have $100 billion. So that's, they can pay each of their neurons $1.
Right. Try
Jeff
to get
Bezos
this
can do that.
idea of how monstrously large that number is. And it's very hard to communicate to humans that number,
It's
a
hard to
billion, much
conceive
less
of.
100 billion. It's just, what?
That's right. And then you think about each of those neurons is connected to thousands of other neurons. And so it forms this massively interconnected web. It's a big network. And they're all sending these signals to each other, these action potentials. But that's the action potential is the binary part of the equation. But there are also analog signals in the brain. So when the neurons connect to each other, they make these little connections of what are called synapses, where they're very close to each other. And a synapse, it converts the electrical impulse into a chemical impulse. There are chemicals that are released into the synapse that can then electrically affect the next neuron in the chain. And that process is a kind of an analog process. The interaction between the chemicals and the neurons can be graded. It can be more or less, and a neuron can integrate. It can do computation by integrating lots of analog signals from other neurons to decide whether or not to fire an action potential. So in some sense, there is this analogy between a computer and a brain, but there's also places where the analogy breaks down.
Right, right. And we have to be a bit careful that we don't lay down framing for what we're looking at that biases what we're looking at. Because, I mean, this is I imagine this is probably one of the biggest challenges of being a neuroscientist and analyzing what you're looking at with the brain scans is, well, we think a certain way, so therefore we're going to interpret these results in that framing, when in fact it could be some other model is going on there that would better explain what's going on, but it's out of sight of us right now because we had a computer revolution, so that's where our heads go with the zeros and the ones, you know. The struggle of this is in a way is itself intriguing, you know.
You're absolutely right. I mean, metaphors are such powerful ways of understanding things. We can apply something we already understand to something that we're struggling to understand. And there's a tremendous power in those metaphors, but they can also be problematic if we get attached to them and we take them too far. And
Yeah,
I think that's
exactly.
actually happened quite a bit in the field of cognitive science, because the computer metaphor is so alluring and it has been so useful. It's also become a bit of a barrier because we've gotten too attached to it.
Exactly. And I wanted to throw that out there for the audience to always kind of keep that in mind as we walk through these things, that this is stuff we're still figuring out as we're going. And so it's still open to new ideas, new thinking, new framing, new ways of looking at it. This isn't like it's all settled and figured out and this is how it is, you know, like this is how you pasteurize milk and there isn't any other way to pasteurize, you know, sort of thing. So, okay, so we got all these neurons up there, 100 billion of them. Are they the workhorses of the brain? Are there other things up there doing work too?
Yeah, so the neurons are thought of as the main sort of information processing units because they generate these electrical signals. But there's also a lot of other cells in the brain that are helping out quite a bit. There are glial cells, and glial cells are the kinds of cells that kind of you think of them as a support system for the neurons. They help to transmit the electrical signals by providing insulation to the neurons. They help to clean up messes that are made in the brain. And a few other things. And, you know, they are probably almost as many, if not more, glial cells than neurons in the brain. We used to think there were many more glial cells in the brain, but that's one of the things, as you say, that can change. Turns out just counting neurons is one of those things that's not totally straightforward. And while we used to think that there were glial cells outnumbered neurons something like 10 to 1, that's no longer the case. And now that seems like they're pretty even in numbers.
Interesting. Do I have it right that the glial or the glia are like the gray matter? That's like when you're looking at the gray stuff, that's what you're kind of looking at?
Well, so not exactly, but the
Okay.
neurons have different parts to them, right? So the neuron has a cell body, just like every cell has a cell body. It's got the nucleus in it. And then they have these cables that are the kind of long, they're called axons, where they send the information. And so the action potential travels along the axon from the cell body to the end of the synapse. And those axons, because they're transmitting these electrical impulses, many of these axons have an insulation around them, the layer of fat that's formed by a glial cell is called myelin. And that helps the nerve signals transmit more rapidly. And that myelin sheath that's around the axons is a fatty substance, and so it's white. And so when you look at the brain, you'll see parts that are white that we call white matter. You'll see parts that are gray that are called gray matter. And really the main difference there is the gray matter contains the cell bodies of the neurons, and the white matter contains the cables that are connecting them. We have the myelin covered cables that are interconnecting the neurons.
Okay, cool. And then the other question I had anatomy wise is then you have, because there's a lot of stuff we can get into, which I really want to avoid, because I mean, admittedly, for lay people, the terminology is a little cryptic. You know what I mean? The median front lobe and the this and the anterior that and temporal lobes. Like what? So kind of avoid all that. But in terms of these building blocks, though, I think this is another thing that gets another term that gets thrown around a lot is neurotransmitters. So I wanted to clarify that for everybody. First off, what is a neurotransmitter, and then how many? I'm kind of curious about them because I've heard that there are some that we don't even have names for yet, or haven't really even fully figured out yet. Is that true, or where are we at with that?
Yeah. Well, a neurotransmitter is a chemical that one neuron uses to communicate with its neighbor. And it's just like a signal. It's a symbol. If one neuron releases a chemical and it has an effect on the next neuron, then they've transmitted a signal to each other. And the way this works is
neurotransmitter.
You got it. The way that works is that the neurotransmitter is released into the synapse, the little gap between the neurons, and it binds to a receptor on the next neuron. And when it binds to that receptor, it's like a lock. It's like a key fitting into a lock, and it activates some kind of a sequence of events in the next neuron. Now, you can imagine that you can have lots of different kinds of locks and lots of different kinds of keys. And it's kind of like the neuron can dump a whole bunch of different keys into the synapse, and they can open whichever locks the next cell happens to have. And we know many of these neurotransmitters. There are dozens of them, if not more. Some of them tend to be associated with specific systems in the brain. And so you might hear different functions ascribed to neurotransmitters. It's really just because they tend to be used in transmitting certain kinds of signals. But really, any chemical could be used as a neurotransmitter. As long as the neuron releases it and there's a receptor there, as long as there's a lock that key opens, you've got a successful neurotransmitter. So in some cases, they're molecules. In some cases, they may even be gases, like nitrous oxide can be used as a neurotransmitter in the brain. And like you say, we almost certainly don't know what all of the chemicals are that are used as neurotransmitters in the brain.
Wow. And these enter in a whole nother level, if I'm understanding this right. These things as chemical reactions between neurons both enable or disable some kind of signaling that's going on. But because there's dozens of different kinds, you can end up with with computers, we have zeros and ones. Everything's zeros and ones, and that's it. It's just on or off. And we combine all these into millions of combinations per second, and you come up with this wide variability of effect as a result of that. But with brains, it's not just a 0 and 1 with a neuron. That neuron can be given, I don't know, let's say 24 different functions or temporary pathways, I guess you could say, for these neurotransmitter networks. So neurotransmitter A is getting, I don't know, let's just be really gross and say an emotional pathway, and neurotransmitter B firing down a line turns on a person moving their finger or something. I mean, it could be two different things regulated by two different neurotransmitters using the same physical network of a bunch of neurons connected together. Is that somewhat right?
Yeah, you can see multiple neurotransmitters used in the same synapse, and you can see the same neurotransmitter used in multiple different brain systems throughout the brain. One of the places where neurotransmitters become important is with drugs. One of the sort of targets for influencing the way the brain works is at the synapse, and that's the way that psychoactive drugs typically work, by affecting neurotransmission at the synapse, by making one neurotransmitter more available, by mimicking the effective neurotransmitter. A drug could fit into that lock in the same way that the key does to activate the receptor directly. So interacting with neurotransmission is one of the main targets of psychopharmacology of drugs.
Interesting. And then, of course, that begs the question, and I'm glad you brought that up because this is something I wanted to get into eventually, is, wow, we're still figuring out what all the neurotransmitters are. This isn't a hit. I'm not taking a jab at anybody. I just wanted to point out, if I understand this right, that we're at a place where we're sort of still figuring this stuff out. And yet we're still coming up with drugs and giving them out to people, and they're taking them and they're doing something. But we're not totally sure what it's going to do to each person. Is that?
Are you leading into the Scientology critique of psychiatry here?
Unfortunately, it is a Scientology critique of psychiatry, but it's not. But Scientology is not the only one saying that.
No, and you're perfectly right. I mean, I don't think there's any offense at all. Especially, I don't think any scientist is offended by the idea that we don't understand things. The mystery of it all is what actually drives us and
right.
and keeps us in business as well. But yes, we understand these systems very little, and a lot of what we do understand is from a process of trial and error. You give this drug to somebody, and you don't. Before you give the drug, you don't know exactly how it's going to interact with the neurotransmitter systems, but you've maybe seen it do something similar, produce a positive effect in animals, and you just try it out to see if it works. So there's a lot of drugs that we know that we have just because we happen to find that they work, and we tend not to design these things from the bottom up, knowing what they're going to do to each neurotransmitter system, because we just don't understand it that well.
Well, exactly. And now that we've covered, I think, enough basic anatomy in terms of the building blocks of this thing, maybe we can actually talk about that a little bit. Like, how does this science move forward? Well, actually, first off, what do you think would be, where are we at? What are the current non-controversial settled science points in regards to what the brain's doing, and that all of neuroscience is basically on the same page? Is it down to the level of, well, we know neurons fire and that's about it, or is it, do we have this more settled than that?
So we have a lot more than that. The field of neuroscience is huge and complicated and multifaceted, partly because neuroscience is something you can study at multiple levels. So you're going to have people that are studying the way individual receptors work, and we're going to know a lot about the chemical pathways that are activated when a particular neurotransmitter binds to a particular receptor. I mean, these receptors are known down to the molecular folding, their individual proteins and the variations on them. There are like 5 different subtypes of dopamine receptors, and we know a lot about what they do in different circumstances.
Wow.
So there's molecular science on that level, and then there's systems level neuroscience that understands a lot of the way the circuitry works and the different specialized circuitries in the brain, to the point where for some neural systems you can predict exactly how they're going to behave. We know certain things about learning and the way fear conditioning works, and the way that the parts of the brain that are recognizing threatening stimuli connect with the parts of the brain that are doing the learning. So we know a lot of the systems level. And then there are neuroscientists like me that study at the cognitive level to try to map really high level cognitive functions onto brain areas. And we have a tremendous amount of knowledge now about the way the cerebral cortex works and how different areas of the brain are specialized. And we have a lot of work now on network neuroscience, understanding the different networks in the brain and how these brain regions interact with each other to produce cognition. So it's a very large field that would be hard to summarize very briefly, because the knowledge is so spread out.
No, of course, that itself is a good summary, because it tells us that there's levels to this. It's not just one amorphous mass that everybody's got under a microscope.
Right.
So, okay, so we have these different systems. I am imagining that we've learned about these through brain imaging. What is that, and how does it work, like at a practical level, and how accurate are these things? Because this is one of the first points of attack is, yeah, but those images aren't that accurate, and they don't really know what they're looking at. How much do we know what we're looking at?
Yeah, I think, well, first of all, any scientific method should be critiqued and is not a foolproof on its own. And we always try to combine across techniques. We try to find convergence with what we find with brain imaging from what we know from, say, animal physiology or anatomy and other levels of study. So we want to find convergences across levels, and not to just trust any one particular methodological technique. But the kind of brain imaging that I do in functional MRI basically uses the same MRI machine that you would find in a hospital if you break your leg or something. You're trying to get an image of the bones. It can produce images of the brain, and we can use that to look at the anatomy of the brain. And one field of study just looks at the anatomy of the brain. We can ask questions about, for example, how does the anatomy of the brain relate to what we know about differences among people? So let's say we're interested in some personal characteristic like intelligence. And we say, well, how does the brain look physically different in people who are more or less intelligent? It's one thing we could do. But what we like to do in my field is look at the function of the brain. And so we use that same magnetic resonance imaging machine to try to infer what's happening in the brain while people do things. And the reason we're able to do that is because when one part of the brain is working very hard, it consumes more energy and it requires more oxygen. And what happens is the brain is very intelligent. It's really an amazing organ. The blood vessels start to change in areas of the brain that are more active, and they route more oxygenated blood to that part of the brain. And so what we see are these changes in blood oxygenation as the brain changes in activity. And we can pick up that signal, that change in blood oxygenation, on the MRI machine. And so we can generate images of where there are changes in brain activity. And we can relate those to what we know the person was doing psychologically at the time.
Totally. Okay, so the fMRI then is not necessarily a snapshot of electrical activity. It's a snapshot or a picture of where we have oxygen going and where and heat, stuff like that.
Oxygenation, and yes, changes in blood oxygenation. So it's sort of an indirect measure of changes in electrical activity, several steps down the line. And it is related to changes in electrical activity in the neurons, but it's an inference that we're making based on changes in blood oxygenation. So it's an indirect measure.
Got it. Okay. And you mentioned this is one of many types of ways of looking at these things?
There are different ways of doing it. You can use, for example, PET imaging, where you inject a radioactive tracer into the brain and you see which neurons take up that tracer. That's a little bit more invasive. We don't really like to use radioactivity if we don't. So fMRI is probably the most popular method of brain imaging nowadays.
Okay, got it. So if you were going to analogize it to a picture, let's say in terms of accuracy or pixel depth or whatever, like how accurate do you think you're getting when you're looking at these fMRIs?
Yeah, that's a good question. Well, there are different kinds of accuracy that we can have. In terms of spatial accuracy, like resolution, if you think of a television screen and you want your television to be as high resolution as possible so that you can really see the detail, it's actually really, really good at that. We can get down to less than a millimeter of resolution a lot of times, which is pretty good for a picture. It's not microscopic resolution. I mean, the neurons themselves are much smaller than that, but it's pretty good for a picture in terms of spatial resolution. What it's not good at is temporal resolution over time. It takes us a while to create these pictures, and because the blood flow responses that are driving them happen very slowly over the order of seconds, it's a picture that tends to collapse across a big period of time and not show us very rapid changes in what's happening in the brain. So kind of a trade-off there between how well we can see spatially and how well we can see across time.
Okay, got it. So as a cognitive neuroscientist, then what are the methods you use? I mean, you mentioned predominantly you're using fMRI. Are there other snapshots or other ways of getting pictures that are faster or more responsive?
Yeah, so one of the other technologies that's pretty common in neuroscience is the electroencephalogram, or EEG. And that's where you basically place sensors or electrodes on the scalp and you measure the electrical activity of the brain through the scalp. EEG has really, really good temporal resolution. You can measure the electrical signals millisecond by millisecond. It has the same trade-off, though, where it's poor at spatial resolution. It's hard to tell exactly where the signals are coming from under the brain because they're diffused through the scalp. So we don't have one technique that's good at everything. We have lots of different techniques that each have their own advantages, and we try to triangulate by using them all.
Right. Sort of like, I don't know, kind of like having an infrared camera with a half a lens hood, taking a picture of a person in a foggy, I don't know, in a foggy field. And there's the guy, we can see him, but it's a little out of focus.
I mean, it's also kind of like trying to infer the shape of a person from looking at the shadows they cast on the wall. And if you look at the shadows that are cast on multiple different walls, you can kind of figure out what the 3D shape of the person is. But no one shadow gives you the whole shape of the person.
Right, exactly. I imagine this might also, if we brought a astrophysicist or astronomer or something in here, they might have similar things with how they get some of those amazing pictures from space of having to combine different radio waves and this and that and the other X-rays and all this other stuff.
Yeah, that's right. And I guess another thing to point out that about those images is very similar to the images that astrophysicists create. They're often using the colors in the images to represent things that are there in reality that you can't really see with the naked eye. And we do the same thing in brain imaging. You're going to see lots of pictures of colorful activations happening in the brain. Obviously, those colors aren't there in the brain, but those colors represent the statistical changes we see in brain activity. And it's always important to keep that in mind, that those are statistical pictures that you see when you're looking at brain images, brain activity images.
Are we looking at such an image behind you then? Like, it's not like there's really neurons lighting up in the brain.
No, that is actually not a statistical image. This is a real picture of just a microscopic picture where the neurons have been stained in a way that makes them light up and makes them individuate from their background. So that's actually really what they look like.
Oh, wow. Okay. So we do get the little lights flashing in there. That's cool.
Yeah.
Okay. I mean, as far as the picture, the representation of it goes, it's kind of cool. Hey, everyone. Most of us are sticking close to home for the time being. So if you haven't signed up for the Great Courses Plus yet, now is the time to do it. The Great Courses gives me a window into real knowledge and understanding of the world that I just haven't found so conveniently anywhere else. It's hard to engage in critical thinking if you don't have the knowledge and resources at your fingertips to get the true data across a wide diversity of fields. With thousands of lectures from the world's best professors and experts, the Great Courses Plus is a great way for everyone to stay informed and engaged. Now it's particularly applicable, since in order to get through these turbulent times, we need to understand our current situation with reliable, fact-based courses like an Introduction to Infectious Diseases to learn about viruses, vaccines, and disease transmission. Money and Banking, what everyone should know to help contextualize the current stock market. Fighting Misinformation, Digital Media Literacy, to help interpret fact from fiction in the news. And then there's the kids, who can use this resource to help learn about math, science, and history while they're out of school. You can also use this time to pick up a new hobby like gardening, cooking, or practicing yoga. Even how to speak a new language. With the Great Courses Plus app, we can watch or listen at any time from a phone, tablet, or internet-connected TV. Now is the perfect time to get started. The Great Courses Plus is giving my listeners a free trial, and it's only $10 a month when you sign up for a quarterly plan. Sign up today using my special URL to get started. Find all the details at thegreatcoursesplus.com/critical. Remember, thegreatcoursesplus.com/critical. So, okay, well, let's talk about this computer analogy in this brain and what this thing is doing. Where do these, where do the analogies work and where do they break down? What are we solid on and what are we like, this part we're guessing or we're not sure or we're trying to figure it out still?
I think it would help.
I know it's a broad question, but
it's a broad question. So let me focus a little bit. I mean, it help if we if we maybe pick one kind of function that the brain does and talk about it a little bit. It might help to clarify that. And one of the things we can talk about is perception, because that is one of the main functions of the brain that kind of dominates our experience. And if we talk about perception a little bit and we can kind of get into some of the misperceptions people have about the way perception works that will give some insights into the way the brain works and how it is different from a computer. So the brain, is trying to figure out what's out there in the outside world. And the way that many people think that this works is by just reading all the sensory information off and putting it together to come up with an idea of what's out there in the world. This is a kind of processing that we call bottom-up processing. You start with the sort of basic sensory information and you piece together an idea of what it is that you're trying to perceive. Imagine if you have a jigsaw puzzle and I just give you all the pieces to the jigsaw puzzle, but you don't see the cover of the box. and you're trying to figure out what it is. You've got all the pieces and you're putting them together, and at some point you start to get an idea of what it is that you're looking at, and you figure it out that way. That's bottom-up processing. And this does happen in the nervous system. So for example, you think about the visual system. You have light coming into the eye. That light interacts with specialized neurons in the retina that convert the light to electrical signals, to the action potentials that we've been talking about. Those action potentials travel back into the brain, to a part of the brain called the thalamus, and eventually to the very back of the head, in a place we call the visual cortex that's involved in processing vision. And each step of the way, as the information travels from one step to the next, we get more and more sophisticated picture of what it is that we're looking at. So some of the initial neurons might respond to things like little dots of light. And then they may be assembled from inputs of multiple neurons. The next neuron could identify a line. And if that neuron feeds into other neurons, that next set of neurons might be able to figure out what kind of a shape is out there. Is it a face? Is it a square? Is it a triangle? This is a bottom-up process of trying to figure out what's out there in the world. And it's the way many people think about perception. But it turns out that this is only half the story, or maybe less than half the story, because we also have a lot of information coming from the top down. The brain is constantly making guesses and generating hypotheses about what it is that's out there in the world to generate a model of the outside world. And if you look at the anatomy of the visual system, you'll actually find all of these top-down connections going from higher up areas of the brain down to the lower areas of the brain. And in fact, if you look at the connections between the visual cortex and the thalamus, many, many more of them come in the top-down direction than in the bottom-up direction. Something like 9 to 1. And that's kind of crazy.
Yeah. What?
Right?
What does this mean, doctor?
So,
I'm loving that we're going in this direction. This is exactly where I wanted to go. So perfect.
I mean, why is that there if we're piecing together information from the bottom up, right? Mm-hmm. It's because we're not just piecing information from the bottom up. The brain is constantly making predictions and imposing those predictions on the information coming in, trying to figure out whether the information coming in fits with its predictions. So the brain is never quite always figuring out the puzzle box without the cover of the box first. It's always starting with some idea of what the cover of the box is, and then asking whether the pieces fit into it. And that interaction between the sort of top-down process and the bottom-up process is really what gives us perception. And there are so many visual illusions you can use to demonstrate this to yourself. Everybody's seen these things where there's two squares and one of them looks dark and one of them looks light based on the context. They're really the same color. The brain is constantly using contextual information to make inferences about what it is that we're perceiving. And this is part of this top-down process that dominates our conscious experience.
Awesome. So in other words, 9 out of 10 of these connections just in this perception circuitry that you're discussing right now are feeding information into this visual system from, now am I making a leap of logic here that what it's feeding into the system or throwing out as potential predictions of what it's actually looking at are based on past experience?
Well, they're based on something. They're based on some knowledge, and that could be past experience. It could be knowledge that the visual system has about the world that's infused in us through evolution. So, for example, we know that light things tend to be darker when there are shadows cast on them. That may not be something you have to learn. That may just be built into your visual system, that the visual system will then adjust to have us perceive something that's in a shadow as lighter because it expects the shadow to be changing the way it looks. So there are things like that are just built in from evolution. And there's also a lot, as you say, from experience. When you walk into your podcasting studio, it's not the first time you've been there. And there's something dark and oblong on the desk. You're not going to spend too much time looking at the details of that to figure out what it is. You're already going to have a guess that there's a microphone there. And it may take very little for your brain to confirm that the microphone is there to give you the experience of the microphone.
Exactly. So if you think about this, because we haven't really broken it down yet, but what we're talking about here is prediction. We're talking about the brain going, okay, I've been in this room before, I've been in this position before, I've been in this situation before. These are the things I'm expecting to see because I've seen them 1,000 times before. And so those are the things that are being fed into this system and then at some point along the line, comparing and contrasting these predictions with what actually came in.
That's exactly right.
Okay.
And the experience that we have is really dominated more by these predictions, by the models that the brain has, than by the information coming in. And there are a lot of ways of proving this to yourself. I don't know if you, one of the demonstrations I like to do in class is, you remember a few years ago, there was that picture going around the internet of the blue and black dress?
Yes. Yes.
And half the people saw this thing as blue and black, and half the people saw it as yellow and white. And if you saw it one way, it was very, very hard to accept that anybody could see it any other way.
Yes.
Because your conscious experience of seeing it is based on this interpretation your brain has settled on, based on some prediction it's made, confirmed by information. And even though people are confronted with the same incoming information, they can generate a different top-down interpretation of what's there and end up on a different perception. That's how we get these warring groups of people on the internet, seeing the same thing, but perceiving something different.
Exactly. And when we make that comparison to a dress, everybody laughs and it's kind of funny. When we make those comparisons between political parties, out come the guns. So it can get a little bit wild how this works, but the mechanisms, at least the basic perception mechanisms, seem to be same.
That's right. And, in the field of perception, as many cognitive scientists have said, that our perception is like a controlled hallucination, because our experience is generated by the brain and not generated by reality. And it is tested against reality to some degree. But knowing that, I think, puts us in the position of wanting to be skeptical of our experience, right? I mean, once you know that the brain is just presenting you this hallucination, and if your listeners are interested, we can provide some links to some of these illusions that we're talking about. They're very convincing. And once you confront this fact, it does give you a necessary skepticism on your own experience, that what is being presented to you by the brain is some kind of a temporary model that needs to be tested against reality.
Exactly. And for those of you who have been wondering why I've said that, because I've sort of taken this up over the last couple of years, last year or two, why I say critical thinking isn't native to our brain or inherent in our systems, so to speak. This is one of the exact things I was thinking of as to why, is because unless you take the time to conscientiously overcome this predictive coding thing that's going on in your brain, you're going to roll with what you think you're supposed to be seeing or hearing or feeling, or whatever other sense you're tasting. And it's only when it's not that, in a really shocking way, you bite into, or you drink the milk and, oh God, it's sour milk. Didn't see that coming, right? But it takes a second. When you first are tasting the milk, according to this model, you'll taste milk, and then it'll take a second, and because your brain's expecting to taste regular milk, right? So it's feeding those predictions into what your perception system. I'm going to make a leap here and say that the visual cortex system and the taste systems probably operate in a similar fashion this way. We expect to taste chocolate when we bite into the Hershey's bar, so our brain preps us for that, based on earlier experiences we've had of that, there's so many things to talk about with this, because it takes a second for the actual perception to kick in, override our prediction, and then we're like, oh, I didn't expect that, right? So that's why there's always a delay. I mean, there's all kinds of things going on here,
Yeah, I think the general principle is that, the brain is not evolved to necessarily generate a model that is as accurate as possible. It's evolved to generate a model that's as useful as possible. And that,
that's right.
The issue about shadows is a good example. We don't necessarily care what the actual light is that's hitting our retina. We care whether we can reasonably consider the color of the thing underneath the shadow to be light or dark. That's just useful to the brain, and so it presents us a a perception that's based on what it thinks it's most useful. And that can
Exactly.
lead to errors.
Well, would you say that this might be the explanation for, or part of the explanation for why it is you can be staring right at something and not see it?
Yes, in fact, one of the examples of this kind of hallucination that I like to draw us to, this is also one that we all sort of experience or don't experience every day, is the blind spot. We literally have a blind spot in each eye where the eye does not receive any information from the world because there are no visual receptors there. So if you close one eye and you look out at the world, there's a part of your visual field that's missing information. And instead of seeing nothing or a black spot or like TV fuzz, we see a continuous picture that the brain presents it to us where it fills in that missing information, kind of like a Photoshop content-aware filter. Just gives us an experience of what's around it.
That's right.
So our visual perception has all of these holes that are pasted over for us, and the brain tries to present to us a coherent, consistent picture of the world. And in doing so, it takes a lot of liberties.
Exactly. And it's not exactly telling us that it's doing that either. It just does it. And this is where, this is why we're actually, this is why we are talking today. Because I want my listeners to know this, and I really want them to understand this at an anatomical level. Like, your brain ain't necessarily the arbiter of objective truth. It is feeding you what you expect to see or hear or taste or whatever, more so than it's feeding you a new vision of, a new perception of the world around you. So and we do see this in all those illusions that we get on social media.
That's right. And this motivation to present a clear and consistent picture appears very strong in the brain. And one of the ways in which we see this with cases of brain damage, we can see sort of extreme cases of this. So the blind spot is a very small spot in our visual field that gets filled in for us. But there are cases where people have big regions of the visual field that are missing because of damage to the visual cortex, and the brain can still fill them in. In fact, there's a complete case, it's a very rare neurological syndrome called Anton syndrome, where people are functionally blind because their visual cortex is damaged, and yet they appear unaware that they're blind because the brain completely confabulates a visual experience for them from scratch.
Wow.
So that's an example of the extent to which the lengths that the brain is willing to go to present us with a hallucination when there's no information there.
Wow, that is fascinating. It starts making a lot of sense, and it certainly made a lot of sense for me when it was pointed out to me. I think Eagleman was the one who pointed this out in his book, that your brain is not seeing anything. It's not hearing anything. It's only receiving neural flows. It's only getting, like, okay, here's the eye, and it's sending it a stream of, neural signals. And it's not actually seeing any light waves. The brain is in a black box. You might as well take it into another room. I mean, it's just not even like it's not getting any of it. It's just receiving these neural signals. So that's kind of startling to think about a little bit, in that it's a kind of its own little black box operation. Because, and I think the usefulness of thinking about it that way is you are then able to sort of remove some of the significance we put on our perceptions and realize that the brain can actually input signals from all kinds of things. I mean, it's not just the eyes and the tongue and the ears that it could potentially be receiving input from. This is where that plasticity thing comes in, right? The brain can mold itself or change itself to receive all kinds of inputs.
Yes, I mean, all of these systems of perception are processes of inference. You're right. We're never just reading off the sensory world. The same thing that we're using vision as an example, but yes, it applies to all of these different senses: touch and hearing. In fact, even to our interoception, to our sense of what's happening within our own bodies. if we think about the importance of the perception of our internal states, it's very important for feeling and emotion. You know, you feel your heart beating really fast, or you feel butterflies in your stomach. Those are feelings that are very important for our emotional life. And they are also part of a cycle of inference. And you can think, if you've ever had any kind of anxiety, or you feel like you're having a heart attack, and then the fact that you're interpreting it that way makes your heart actually beat faster, and you get caught in one of these cycles, you know exactly how important this process of inference is. And yes, it's not only limited to our perception of the outside world. It's limited. It seems to be a general process that's involved in any kind of perception that the brain does.
It's a magnificent discovery, because the predictive coding thing, this idea that the brain is constantly predicting what's going to be happening and putting that on you, you know, as this is how reality actually is. Well, maybe. I mean, I'm curious, how do you see this as affecting cognition, as affecting our ability to perceive reality versus what we sort of think is reality?
Well, it's a very effective system. I mean, it actually is very good. I mean, one of the things that the brain is really good at doing is gathering large amounts of information and using that to efficiently process the world. The world is so complicated, and there's so much information out there in all the different senses. If you think about how complicated the visual world is, and at the same time you're being bombarded by sound and by touch, and by touch is actually a composite of 5 or 6 different senses, because you have vibration and pressure and all these different things, and pain.
Oh,
and
good point. That's right.
That if you were to actually try to process all of this stuff from the bottom up, it would be a mess. So directing our perception based on our current goals and making it hypothesis driven is an ingenious engineering decision by nature. To make it this way, because it's incredible that we can walk into a room and immediately know what's there without having to process it all from the beginning.
I absolutely. It makes complete sense once it's explained. And yet it seems to be one of the most counterintuitive things about us that we've discovered so far, because we don't think the way we think we think. And it really kind of you go, well, if I was going to design this system, yeah, this makes complete sense. But up until we discovered it, we thought, oh no, we're getting all these perceptions and they have to be processed before we can act and all of this. And yet when you do the math, you'd see no major league ball hitter would ever be able to hit a ball ever, coming, because they come so fast that it's too fast for the brain to sit there and bottom up process how this particular individual pitch is coming in. Yeah. This is why you have to, this is where muscle memory and practice and all of that come into play.
Prediction plays an important part in motor control, as you say. I mean, the brain doesn't want to wait for the sensory feedback from the muscles to know whether a movement was successful or not. So it models that and makes a prediction about how it's going to feel when I swing that bat, so that when it starts to happen, I can already make an adjustment on mine before I even get that sensory feedback.
Yeah, exactly.
It's an ingenious system.
It really is. It's the only thing that allows us to actually live. I mean, so it is quite a smart thing. Now I'm going to harp on the inadequacies of it, of course, though, because there are cognitive problems with this, because we have placed demands on our brain that go beyond physical necessities. I mean, we gather, we hunt, we grow stuff. Great. But now we're like trying to be rational creatures that make ethical, moral decisions based on logical frameworks. And this ain't what this is all about. So how is this kind of, we're sort of tripping over ourselves a little bit with this too. How do you see that?
Yes. I mean, from one perspective, this is what the process of science is designed to counteract. If you're in the search for objective knowledge, one of the first things you realize, if you're really concerned with getting to the truth, is that you have to put in place some kind of procedures for separating your own biases from the outcomes that you're looking at. And that's really what the mechanisms of science are about. And if we're going to do an experiment, we want to make sure that we're, say, blind to which person we give the drug to, because we know that if we know this, it's going to bias us. And so we have all of these very specific technologies within science to separate our biases from the actual truth. But these are not things that people implement in their daily lives for the most part, right? So we walk around forming beliefs, and most of the time our reasoning is driven by all kinds of biases that we're not aware of and motivations. And that's why I think it is important for us to have this conversation to try to uproot some of those biases. The more we're aware of them, the more that we recognize our cognition is motivated, the better we can do at mitigating the effects of that motivation. But
Exactly.
the first step is recognizing it, right? That we aren't just cold computers, that everything we do is motivated by something.
That's right. And that motivation is important. There's a term, motivated reasoning, in cognitive psychology. And I've, of course, talked about it often in terms of bias, negative biases. I'm always fighting against, negative kind of biases, prejudice, discrimination, cult thinking, extremist thinking. But these are the extremist ends of a mechanism that we actually do need for our survival, as we're laying out here. How, from a neuroscience point of view, how have you guys been approaching, or has anybody been approaching this yet from the point of view of, is there a way to temper that, or is there a way to deal with that so that we, so these extremist mindsets, that we can somehow discourage that or fight back against that? Because it looks from empirically to be a fairly common trait of humanity, that we, take a perception or a belief and we just run with it,
Right.
without thinking, right?
Absolutely. I mean, I think it's of great concern to cognitive psychologists and social psychologists now to understand how this works and figure out ways to mitigate it. Especially, we've seen this kind of cognition be amplified by the internet recently, and by the kinds of information flow and social networking that we see on the internet. And so there's a tremendous amount of research covering this from all different angles. The way that I like to come at it is by understanding the basic, what are the basic mechanisms? What are the sort of pieces of the machinery that cause us to function this way? And we've talked about some of them today in the predictive coding. And the other big piece of this that we spend our time looking at is the social piece, because one of the main motivators for the kind of extremism that you're talking about is social connectedness, and wanting to feel part of a group and sharing information within a group. It turns out that these models that we build of the world, they don't exist within just one individual brain. They tend to be shared, right? We have shared models of the world that are transmitted culturally. And there's a value in that. There's a value in sharing our models so that we make similar predictions about the world, and that a prediction that you make can help a prediction that I make. So there's a value there. And at some point in our evolutionary history, it might have been really, really, really important that we share our mental models of the world. And so it's built into us to feel really good about that when we can share a belief with someone else. And so it may be that one of the important functions of a belief is to promote social bonding between people when we share those beliefs, right? But then again, as you say, there are some side effects of this in the modern world, which is that these things can get out of control.
Yeah, exactly. It's kind of like nature goes, okay, well, here's something I want to be able to do. Have social hierarchies. Yeah, let's do that. Okay. Well, let's build this and this and this into it so we can do that. Share ideas, share whole structures, right? Through, it's in your brain, now it's in my brain. And now we have this common view of things. Lower life forms don't get to do that. But it seems like the trade-off is at the same time, okay, well, we'll give you this ability, but the bad side of the coin is you can run with it too far. And
yeah, and the models become harder to change once they're shared among people. Right. If you have a mental model within yourself that you encounter some information that needs suggests the model should be updated, you can do that. But it becomes harder when, in order to update the model, you also have to update everyone else's model, or to change your relationship with everyone else. And that's a much bigger task. And so The fact that mental models are shared among people makes them more stable and more sticky, harder to change.
Yes, big time. Wouldn't it be something if we had automatic updates of everybody in our social life, like in our own brain? Like you could just kind of upload
Right.
oh,
Like
this
we do
is
with
where
our
Bill is
phones.
at now. Bill changed his mind about that now. Here it is. Here's the update.
Yeah.
You constantly have a present time reflection of your social hierarchies and stuff. It'd probably change some things. Let's see. I wanted to ask about another structural point. Is it structurally, like from what you understand about brain anatomy and networks and how they're put together, something I've been thinking about a lot in the last couple of months is how just how overwhelmingly important our childhood is to our development. I'm far from the first person who had that thought, but I've wondered about the significance of the fact that we don't even remember most of the most basic, fundamental first times we experienced almost anything. From the first time we experienced chocolate, to the first time we read a word, to the first time that we went, even first day of school, most people don't even remember. And yet, the neurons didn't forget, right? Or did they? What's going, like, these deeper memory? I guess we're trying to talk about memory here a little bit, and I know this is a huge topic. But are those lower, more basic memories that we don't even remember anymore, are they still there? Like, how does that work? Because those are the most basic foundations of all of our biases, all of our views.
Yes. I mean, I think that's the first one of the lessons from cognitive neuroscience is that memory is not a unitary phenomenon. That there are different kinds of memories, and there are different neural systems that support different kinds of memory. So there are memories we have that are explicit, that we can tell you, I remember the first episode when I first rode a bike. And then I might forget the first time I rode a bike, but still be able to ride a bike because I have the kind of memory that allows my muscles to coordinate in that way. So there's a period of childhood amnesia. In the first few years of life, most people tend not to remember their experiences in an explicit way. But yes, that doesn't mean that the things that we implicitly learned during that time aren't still there. I mean, surely they are. We learn how to walk, and we can still do that, right? Even though we don't remember the experience of walking. But in terms of belief and explicit belief, I like to think of it as kind of like a house that we build throughout our lifetimes. And you start with a sort of a foundation that you build, and over time you kind of add little pieces, and you might make little additions to your house, and you might forget that the foundation is there, but the whole thing rests on that foundation. And changing that foundation can involve changing the entire house. So it becomes difficult to change some of the earliest models of the world that we have formed.
Big time. And I think my own experience is certainly for me indicative of that. Grew up in a destructive cult. So the basic memories that were laid down for me, the basic beliefs of how life works, how it's structured, that we're spiritual entities, not just these physical bodies, that L. Ron Hubbard's a great guy, right? These sort of, foundational sort of beliefs that get laid in when I was 4, 5, 6, 7 years old that I have no real recall of. 40, I hit 42 years old, 43 years old. I come out of that situation and I got to relook at everything. But is it even possible for me to relook at everything? I mean, when you go all the way down to the bottom, is it even possible to rework some of those foundational ideas,
Yeah, there might be sort of deep implicit feelings you have about L. Ron Hubbard that might not go away, even though you change your explicit model of him, right?
That's right.
So in that way, it becomes very, very difficult to change things that were conditioned into you earlier on. Conditioning is another form of learning. If you constantly associate one thing with a certain kind of emotional response, that association is there, and it's not an association you can erase just by recognizing that it's there or by recognizing that it shouldn't be there.
Exactly. If only, if only it was that easy.
Right.
And that's actually something I'd love to do. One of the things definitely would like to do a future episode about is memory and these different forms of memory and where we're at with memory, because I know this is a subject of intense amounts of research, and I am most curious about them. Hubbard, of course, had it totally wrong, because his take from 1950 was, and I think this was not an uncommon belief at the time, was that you had the potential to remember everything that's ever happened to you ever. It's all there. We just got to get to it, right? But we've
Right.
since,
Even
of
in your
course, learned.
past lives.
Yes. Yes. Yeah. And that, of course, is just completely spiritually structured. There's not even an effort in Scientology to claim that your past lives are stored here. That's a whole different thing. But all of this life is supposed to be completely available to you, you know. Clearly not.
Interesting.
Clearly not the case. Yeah.
No.
And I'm fascinated by that whole area. I don't want to go much longer. I think we've covered some basics that we needed to cover. I know some of it was a little more, like maybe some people are like, yeah, I know that already, but not everybody does, guys. So just be patient with us here, because we're building a foundation here for this series that we're doing. Cognitively, where are we at theory-wise as far as like are there theories of what thinking is, what rational thought is versus emotion? Are these things separated, or are they just thought of as, these are just different neural networks and that's all there is to it? You know what I mean?
think that's, one of the things we've learned is that when you try to separate rational thought from emotional thought, it's always an artificial separation. That emotion really is infused in almost every cognitive process that we have. And it makes sense. You think about what emotion is, we should, sort of, to understand this, really have to define emotion. And emotion really is rooted in some of the basic homeostatic mechanisms of the body, some of the systems we have for keeping ourselves alive. So you see a bear and your heart rate's going to go up and your pupils are going to dilate and your body's going to prepare all of the activity it's got to do to save yourself from that bear. And that is the emotion of fear. There's also a conscious experience that comes along with that, of noticing that your heart is racing faster and that there's a bear there that you want to get away from. And we in our lab, we distinguish between emotions and feelings, where feelings are the sort of conscious experiences of these internal things happening in the body. And these conscious experiences of these feelings are important for every kind of cognitive process that we do. Even if you're thinking about the most abstract math problem, at some point you may have a feeling that you're onto the right path, and you engage in certain cognitive operations because that feeling encourages you to go there, right? We know that people who have damage to the brain that leaves them unable to feel and to incorporate feeling and emotion into their decision-making process, they make really bad decisions. They don't turn into purely super AI robots. What happens is they are kind of a mess, and they can't use the feelings that we all use to predict risk and reward as part of their decision-making process, and so they make bad decisions. So emotion is totally intertwined with rational thought. It isn't really separable in any real human being. And so the questions for us are sort of more about what the role emotion plays in rational thought and how the interactions happen, rather than whether or not they do.
Yeah, exactly. I again, fascinated by this because of Hubbard. Hubbard had a whole system with emotions and an emotional scale that he plotted them on, with numerical assignments for each emotion and a graduated scale of positive emotions, negative emotions, all this kind of thing. Again, 1950, 1951. I mean, really,
I wish we could have taken that motivation he had and funneled it into actual cognitive science. I mean, he could have made
right. Exactly. Yeah, pretty, but the subject of emotions, of course, something people have been wondering about for millennia. I'm glad you mentioned that there really, is not a whole lot of difference in terms of what's going on up here. It is an artificial differentiation we make. I think going back to the Greek tradition, probably, the passions and the things are going to get the blood going, and it's like, oh no, let's not do that. Let's be rational today. Well, actually, you're being rational the whole time. It's just different things going on there.
That's right. And if you think about rational also in terms of the intelligence that's embedded with it, and emotions are not an unintelligent system. They're very intelligent. They have within them all of the knowledge of evolution that is a very rational system in the sense that it is using and integrating a whole bunch of information that we may not be consciously aware of to direct us to do things that are very advantageous for us.
I love how you put that, because when you look at the fear response, your blood starts racing, your heart's going faster, your lungs are picking up speed. Why? Because your body needs to move quickly.
Right, exactly.
Like that's your body, you don't have to think about that. It just happens. That's what you want happening. Like this is, again, this is where this prediction is a feature, not a bug. But there are instances and circumstances we've now created with the way our societies run and the way our culture is put together, where it can be a bug if it's an inappropriate response, and that's where we're caught, and here we are having this conversation today. So
exactly.
Yeah, fascinating stuff. I want to get into more details about some of these mechanisms in future episodes and talk about the pros and cons, features and bugs of them, from the neuroscience point of view. I think we're probably going to have to wrap up our episode now in terms of time. Just so you guys know out there, I've got a list of about 10 things that we've already talked about talking about. So we've got a lot more future content here, but let me just ask you this to wrap up: are there other basic anatomy or functional points that we should cover here now to set up for, where we're going that we didn't cover that I might have missed?
No, I think we did a good job of telling people, there's the basics of the way a neuron works and the way signals are sent in the nervous system based on electricity. And I think we did a good job of balancing the usefulness of the computer metaphor against the living, blood-infused, fleshy nature of the brain. And then we talked a little bit about some of the principles of perception. So I think that was a good start.
Excellent. Yeah, me too. I'm glad, and I'm really glad we hit on that predictive coding thing and to the degree that we did. And we're going to get more into that because there's a lot of corollaries there to critical thinking, to perception, to extremist beliefs. I mean, there's a lot going on there. And this is something, do I have this right, that this whole predictive coding modeling is something about 10 years old?
Well, I think the idea that the brain is doing a lot of perceptions through this top-down hypothesis testing is much older than that. I think in recent years, there have been better sort of mathematical models of the way this might work that have become really popular and much more recent and modern. And this sort of the term predictive coding has come into fashion in the last 5 to 10 years.
Okay, great. I like having, done enough work on this that I feel like I can talk intelligently about some aspect of it.
Oh, you definitely have. Yeah.
Oh, cool. Yeah. And I'm interested in what other things are coming out on the cutting edge of this technology as well. So like I said, we'll get into all that. Doctor, thank you very much for taking some time to talk to my viewers about this stuff. I really appreciate it. And I like I said, I think we set up some good future stuff here.
Yeah, thank you for having me. I definitely enjoyed it.
Awesome. If people want to reach out to you directly as a result of the show here, what would be the best way for them to do so?
First of all, they can follow me on Twitter at Jonas_Kaplan. And I guess you can always send me a message on there. It's probably the easiest way to do it.
Beautiful. Okay, good, guys. So I'll put that Twitter link below in the show notes. If you have any questions, comments, or feedback on this for Dr. Kaplan, for me, or just in general, please leave it in the comments section on YouTube or at sensiblyspeaking.com. I very, very much Look forward to your feedback, good, bad, or sideways. I just don't appreciate being insulted. So please don't insult me or my guest in the comments, as some people are wont to do. For the most part, you guys are great, and we don't get too much trouble on my channel. But
you can insult me. I don't care.
Okay, cool. All right, guys. I will see you next week. Bye-bye.